All right, so thank you everyone for joining us today for Ali's defense. Ali has been at UCF for the last 4 years, and he's going to today present his dissertation on understanding the Android ecosystem through some statistical analysis and machine learning work for mapping.
Yes.
And so, Ali, you would have 40 minutes tops to present your. Then we will have questions and answers. The way that we'll do it is that we will have first the committee members, and we will have the public if there's any question. Then we will have a private questioning, and then we will put you for a waiting room, and then bring you back for recommendations and decision. With that, take it from here, Ali.
Thank you so much, Professor Mahason, for the introduction. And hello, everyone. I would like to thank all the committee members for their help and support. And thank you, everyone else, for attending. My name is Ali Alkinoon, and today I'm going to present my dissertation defense titled Revisiting Android Permissions Evolution Through Temporal Analysis, a Data-Driven Study of Behaviors and Implications. So a brief background about me. I'm currently a PhD candidate in computer science at UCF. I've been working with Professor David Mahason since 2021. Thank you, Professor, for all your help and efforts. I completed my master's degree here at UCF in 2023. Before that, I earned my bachelor's degree in computer and information systems from Eastern Florida State College in 2021. This fall, I'll be joining the computer science department here at UCF as a lecturer. I'm very excited for this opportunity and this position. My main research interests are in the security and privacy of Android applications. I'm also interested in machine learning and natural language understanding. Here's the overall outline of this presentation. First, I will provide a concise introduction to the background and motivation behind this work. Then I will present Troy, a temporal and cross-sectional Android dataset. After that, I will discuss Pandora Box, which provides insights into Android permissions. I will then move on from Pandora Box to Clarity, where we'll explore NLP for Android privacy policies. Finally, then, I will summarize the main findings and implications of our study and address any remaining questions or concerns. Now, let's dive into the background and motivation of this defense. So, Android leads as the world's most popular mobile operating system with roughly 3.3 billion devices and 3.9 million applications. This combination with a massive user base and a huge app ecosystem makes Android an attractive and easy target for malware. Now, with Android malware, it poses several serious security risks that include data breaches. This refers to cases where malware can steal sensitive information like banking credentials and private messages. Another one is privacy violations. In some cases, apps misuse permissions to gather user data. Financial fraud, this is the type of malware that can carry out unauthorized transactions, trigger SMS fraud, or run ad fraud campaigns. Now, Android is a major malware target. We want to look at 4 real cases where each different attack methods. Starting with Joker malware that's still ongoing that has infected over 500,000 devices, hiding in Google Play apps to steal SMS data and enroll users in paid subscriptions. Flubot which was spread via phishing SMS, stealing banking credentials from thousands of victims across Europe. And with Trojan, which is still present, targeted over 350 banking applications, using keylogging and disguising itself as a legitimate application. Pegasus spyware, which exploited zero-click vulnerabilities, spying on high-profile individuals globally. These cases demonstrate the persistent and evolving nature of Android malware threats. Here's a quick example of how Android malware spreads. Users install apps, often anywhere they might be interacting with fake or malicious versions. Attackers disguise malicious apps to look like real apps and distribute them online. Once installed, the APK infects the device and can access sensitive data or device function. Now, let's break down the APK itself. These core components matter for how malware operates. The manifest file defines app permissions and metadata, which malware can abuse. Text files carry out the Java bytecode that actually runs the apps. Then we have resources that provide things like UI elements and native libraries that add performance boosts. Why this matters is because APKs are crucial for app distribution, but that same mechanism can be used to exploit to deliver malware. Now, diving to our first piece of this dissertation, Troy. Now, for the motivation for this work is that a major challenge in Android malware research is the lack of modern, reliable datasets. Most existing datasets like Driven, Genome, and AMD are outdated. They don't reflect today's malware behaviors or evolving attack vectors. Many are also missing metadata like permissions, API code, or privacy policies. And accessibility is limited. Some are either restricted or no longer publicly available. Our goal is to build a comprehensive, up-to-date datasets. We collect malware samples from 2019 to 2023, capturing modern threats. We extract over 39 metadata features per sample to support deep behavioral analysis. And we made the data set publicly available on Databoard so other researchers can freely use it and build on top of it. Let's walk through the main contributions of our dataset. First, it's comprehensive. We collect about 5K total applications, both malware and benign. Second, we include rich metadata with 39 different features like ads, rating, permissions, and in-app purchases. We also extract extensive static artifacts such as CFGs, API calls, functions, and among many others. For classification, we labeled the apps using virus total, and we used AB class to group the malware into known families. Finally, our data set spans 5 years, so it captures malware evolution and supports long-term studies on security trends. Our methodology follows a step-by-step process for building and labeling the dataset. First, we collect Android applications from Android, a public APK repository. Then we extract both metadata and static code features. After that, we clean the data and standardize the formats. This includes organizing feature types and genres. Next, we send the apps to VirusTotal, which scans them using over 70 antivirus engines. Finally, we use AB class to group the malware samples into families, which help us analyze broader attack trends. Now, with collecting APKs, it's not straightforward. There are multiple barriers. The first thing is Google Play does not allow direct APK downloads for research, so access is restricted. Second, privacy and legal restrictions block scraping, especially for region-locked or sensitive apps. Third, there are commercial limits. Some apps are private, paid, or explicitly block access for research. To overcome this, we use Android, a public APK dataset collected from third-party resources. We cross-validate apps metadata and the apps themselves to check if they're still available on the Play Store. For our selection criteria, we defined a clear selection criteria for the apps we wanted to include. First, we wanted the apps to be chosen from the Google Play Store market and span the years of 2019 to 2023 for temporal studies. We made sure to cover 16 different app genres for variety. So initially, we collected 7,500 applications. Then we cross-validated the apps to check whether they're still on the Google Play Store at the time of collection. That led us to remove about roughly 2K apps that were no longer accessible, leaving us with a final data set of 5,028 applications. Here's an overview of the genre distribution in our dataset. The most common genres in our dataset and the big ones were games, finance, business, and education. This variety helps us ensure our dataset captures different app behaviors and use cases across the Android ecosystem. Now, after we collected the apps, we move on to malware classifications. We want to classify whether an app is malicious or not. We used VirusTotal. VirusTotal works by scanning each APK using over 70 antivirus engines. In our approach, if at least one engine flagged the app, we label it as malicious. If no engines flagged it, we consider it as benign. And then we see a result of 11.2% of the apps, which is 563 out of the 5K were flagged as malware. Here we break down how malware is distributed across our datasets. While we do see malicious apps each year, if we take a closer look, we can see that year by year, there is a clear trend that the percentage of malware has been gradually decreasing over time. After labeling apps as malicious, the next step is to organize them into meaningful malware families. For that, we use the AB class, which helps clean and standardize raw VirusTotal labels. The process starts by collecting raw malware labels from VirusTotal. Then it removes vendor-specific prefixes like company names that don't add value. After that, it eliminates generic terms like Android or Trojan, which are too broad. Next, it clusters similar malware labels together based on naming patterns. And it finally maps these clusters to standardized malware families. Using this pipeline, we identified 76 malware families, including major types like Trojans, adware, and ransomware. You can see examples here like Spino, Joker, and Furball mapped under these categories. After, we crawled metadata for each app to enrich the dataset. This includes things like installs, genre, and in-app purchases, and among many others. We also consolidated categories, for example, merging puzzle and arcade into single game groups. Finally, we selected the 39 most useful features that are security relevant and useful for various applications. Here's an example of the metadata we collected for each app. It can include things like user rating, install counts, developer info, and many interesting things. After we collected the metadata, we collected 8 other features as part of our datasets that enables researchers to conduct various studies based on these features. First is metadata. As we said, it gives context beyond app functionality like ratings, reviews, and among many others. Data was collected using the Google Play Scraper, ensuring information is sourced directly from the official store. Next is privacy policies. These documents explain how apps collect and use our data, providing transparency and helping identify risky behaviors. We extracted those with beautiful soup and we saved them as a TXT file. Third is functions, which outline how an app operates, providing insights into its structure and execution flow. We extracted those with Radar2 and stored it as a CSV file. Fourth is hex dumps binaries, which represents the low-level machine instructions that dictate app execution. We extracted that with Radar2 and stored it as a TXT format. Fifth is strings, which often store embedded data such as hard-coded URLs, encryption keys, or sensitive information. We extracted those with Radar2 and stored them as a CSV format. Now moving to our sixth and seventh, which are permissions and API calls. Permissions, they define what system resources an app can access, such as the camera, location, or context. Here, API calls determine how an app interacts with the system and external services. We extracted those using JetX and Radar2 and stored them as a CSV file. And lastly, CFGs. Control flow graphs visualize the execution flow of an app, showing how different parts of the code interact. It's useful for understanding app logic, identifying malicious behavior, and detecting abusification techniques. We extracted that with APK tool, JetX, and started as a dot file. Here is an example of how the 8 extracted features can be applied in research. Two key areas are static analysis and malware detection, both which benefit directly from this rich feature set. Let me briefly go over some of the limitations of our dataset. First, some apps may no longer be on Google Play when using this dataset. Second, metadata dynamics like ratings or ads can change over time, impacting consistency. Also, the dataset is Android only, so it doesn't support cross-platform analysis with iOS or Windows. And it might not meet all research needs depending on the use case, despite its size. And since we only extract static features, dynamic behaviors like runtime activities aren't captured. Lastly, because malware evolves quickly, keeping datasets up to date is essential to stay relevant. To wrap up, this project introduced Troll, a metadata-rich dataset created to support Android malware research. It contains both benign and malware samples collected from the Google Play and Android Zoo. Each app is labeled using VirusTotal and classified into families using AB class. We extract static features like permissions API calls. We also extracted metadata features that include ratings, ad presence, privacy policies. And then finally, this dataset is designed to enable diverse research efforts across security and behavioral profiling. Now dive into our second work of this dissertation, Pandora Box. Now for the introduction for this work, Android leads the mobile operating system with over 70% share, making permissions central to app security. Permissions control access to sensitive data like location, storage, camera, and network. Now with improper permissions, they can lead to data leaks, unauthorized access, and privacy violations. For example, a flashlight ad requesting location access is a clear red flag. In this case, a user installs an app. The app sends permission request to access system resources that unnecessarily request access via location. This exposes users to privacy risk as data can be used for tracking or surveillance. Now, for the motivation, existing research on Android permission is still limited. Many works either focus on malicious or benign apps, but rarely on both. Few explore how permissions relate to app features like ads or purchases, and prior studies often skip proper categorization. Also, many datasets are outdated and don't reflect recent trends. So, our study filled these gaps by analyzing a recent dataset from the Google Play Store, covering both benign and malicious apps across 16 genres. Our work contributes to a detailed permission analysis across benign and malicious apps. We analyzed over 5,000 applications from the Google Play Store and grouped 321 permissions into 10 semantic categories. We then looked at permission trends by year and across genres, also based on meta features like ads or installs, and finally used FP growth algorithm to find common permission group patterns. This slide shows our overall workflow. We began by collecting APKs from Android Zoo and Google Play, the Google Play Store. Then we classified them as benign or malicious using VirusTotal. We next extract metadata like ratings and installs, and we also extract permissions. Then these permissions are grouped into high-level categories like communication or location. Finally, we analyze trends over time across genres, track permission set growth, and combine features to evaluate permission behavior. Let's take a moment to understand the types of permissions Android requests when accessing a system. There are two main types: normal permissions that are low risk and granted automatically. Dangerous permissions involve sensitive data like location or contacts and require user approval. To illustrate this, we show an example using the app X Survive, as you can see below. You can see the app requests multiple permissions. From these permissions, access network state and update device stat fall under the normal category. Others, like read contacts or access file location, are dangerous and need consent. This distinction is key in our analysis of benign versus malicious app behavior. This slide gives us a breakdown of the permissions we extracted from our dataset. We've analyzed over 5,000 applications, including benign and malicious. In total, we pulled more than 60,000 permission requests from these apps. Over 58,000 came from benign apps, while around 5,300 were from the malicious ones. On average, benign apps requested about 14 permission per app. Malicious apps had a slightly higher average, about 16 per app. Across all the apps, we observed over 300 unique permissions in use. After we collected the permissions, we applied categorization. Raw permissions lists are often too long and difficult to interrupt directly. To simplify the analysis, we grouped permissions based on similar functionality. This helped us reduce complexity and make comparisons clear. For instance, permissions like record audio and camera would fall under the media and camera group. Similarly, send and read SMS are categorized under communication and messaging. We applied categorization by using the official Android developer site to collect and define the permissions. This gave us a clear, standardized description for each permission. We then used large language models and semantic clustering to group similar permissions based on their meaning, as we've seen in the previous example. We follow up with manual checks to make sure each permission was categorized accurately and appropriately. On the right, you can see our 10 final high-level categories, with system and device management being the largest group. Now we move to our analysis of this work. This slide shows the yearly distribution of selected permissions from 2019 to 23 and comparing benign versus malicious apps. We can see from the table the top 3 requested permissions across all the years are access network state, prime location, and course locations. These fall under 2 dominant categories: location and GPS, which is used for tracking and location-based features, network and connectivity needed for internet access and communication. We observe a clear drop in how often malicious apps request these permissions over time. For instance, requests for access file location fell from over 100 to 2019 to just over 30 in 2023. Similarly, access network state have dropped nearly 100 to under 30. As a takeaway, while location and network permissions remain the most requested, malicious apps show a clear downward trend in how often they request these permissions. Now, this slide compares permission usage across the 16 genres against malicious and benign applications. We observed that genres like finance, business, education, games, and others request the most permissions. These rely heavy on location, network, and system access for transaction and real-time updates and gameplay mechanics. In contrast, genres like books, music, and travel request fewer permissions since they often work offline. Notably, across all genres, malicious apps consistently request fewer permissions than benign ones. As a takeaway, regardless of the genres, benign apps tend to request more permissions than their malicious counterparts. We now evaluate how different app features relate to permission requests across benign and malicious apps. This analysis specifically looks how ad support impacts permission behavior. We split apps into ad-supported and non-ad groups. Looking at the graph, we see that malicious apps with ads, shown in red, request more permissions than benign apps with ads, highlighted in yellow, especially in 2023. Even without ads, malicious apps, shown in purple, still request more permission than benign ones, shown in black. So ad presence alone doesn't explain the high permission usage in malicious apps. As a takeaway, malicious apps, whether ad-supported or ad-free, constantly request more permissions than benign ones. Next, we look at in-app purchases. We compared apps with in-app purchases to those without. Looking at the graph, we see that malicious with in-app purchases, shown in red, request far more permissions than benign ones, highlighted in yellow. This gap grows sharply in 22 and 23, with a clear spike in red bars. Even apps without purchases follow the same pattern. Malicious ones, highlighted in purple, requested more permissions than benign ones, highlighted in black. As a takeaway, malicious apps, whether they have in-app purchases or not, they request more permissions than benign ones. Now we look at the install counts, which reflect how widely an app is downloaded. We group those apps in 3 tiers: 0 to 10K, 10K to 500K, more than 500K downloads. Then we compared those across benign and malicious apps in each year group. We can see below that malicious apps in the 10K to 500K range, shown in purple, request the highest number of permissions, even more than high download apps. In contrast, High download apps shown in yellow show a decrease in permission requests over time for both benign and malicious apps. As a takeaway, mid-range malicious apps tend to be the most permission heavy, while benign apps stay relatively stable across all install ranges. After that, we looked at content ratings, which indicate the intended age group for the app users. We grouped the apps by their rating. We started with teen, which is intended for ages 15 to 17, have mature for 17 and plus, everyone that's 10 and plus, and we also have an everyone, which is intended and safe for all ages. You can see below, benign apps generally request more permissions, mainly because there are more of them overall. The peak for benign apps was in 2023, while malicious apps peaked in 2019. The everyone category has the largest number of apps permission requests across both benign and malicious groups. As a takeaway, benign apps request more permissions due to higher volume, and the everyone category dominates in both app types. After that, we looked at star ratings, which represents user feedback and ranges from 0 to 5 stars. We compared permissions across star ratings. So we can see in the graph, benign requests more permissions overall due to higher app volume. In the benign groups, apps with 0 stars and 4 stars request the most permissions. This explains to that such 0-star apps may be new or lack enough user feedback, while 4-star apps are often feature-rich and require more access. Notably, 0-star apps request the most permission across both benign and malicious apps. As a takeaway, users should be particularly cautious when installing unrated apps, as they might not have community validation or have not been vetted yet. Finally, app sizes reflect how much storage or functionality the app includes. We classified our apps into 4 categories: 0 to 10, 10 to 15, 25 to 50, and 50 plus megabytes. We analyzed how app sizes relate to permissions. We saw that medium and large malicious apps request the most permissions overall, especially in 2023. Large malicious apps show a noticeable spike in 2023, reaching 28 permission requests. As a takeaway, large malicious apps request significantly more permissions than especially recently, while benign apps stay consistent across all sizes. We now shift from analyzing individual permissions to examine how permissions are grouped together across apps. To do this, we applied FP growth, a pattern mining algorithm designed to find frequent permission combinations. It's more efficient than a priori, since it skips generating candidate sets. It directly builds a compact FP tree. I'll follow up with an example of how this works in details. We set a 50% threshold, meaning we only keep permission groups that appear in at least half of these apps, ensuring the patterns are meaningful and not rare edge cases. This slide shows an example of how association rule mining is done on app permissions. We start with 3 apps, each requesting different permissions. Step 1 is we count how often each permission appears across the apps. Step 2, permissions are organized into a tree based on their frequency. Step 3, we extract rules, showing which permissions tend to appear together. For instance, access find location shows up in all 3 apps and has strong support. This could, for example, lead to a rule like if an app requests internet, it will most likely also request access find location. In this analysis, we explored how permissions are grouped together in benign versus malicious apps for the whole dataset. Looking at the table, we see 2 things: average support and total count. Average support here shows how often a permission set appears across the dataset. It's always above 50 due to our threshold. Total count reflects the actual number of times each set occurs. From the table, we see that benign apps typically request larger permission sets, often 4 or more permissions. In contrast, malicious apps usually have smaller sets, rarely exceeding 3 permissions. We analyzed how permissions and combinations evolved from 2019 to 2023 in benign and malicious applications. Benign apps, we saw that constantly request larger permission sets, likely due to increased functionality or feature complexity over time. Malicious apps, on the other hand, have used fewer large permission sets since 2020. This may indicate shifts in deployment tactics, evasion methods, or adaptation to stricter security policies. Now, with this analysis, it compares permission set sizes across different app genres. We saw that benign apps request large permission sets, especially in categories like books, entertainment, business, and travel. Malicious apps concentrate in high-risk genres, such as communication, games, music, shopping, and sports. These involve frequent user input, sensitive data, or financial activity that makes them attractive targets for malware. As a takeaway, users should be cautious with apps in high-risk genres and review permission requests before installing. To summarize, we conducted a broad analysis of Android app permissions. We also examined trends over time, app genres for both benign and malicious applications. We also explored how app permissions relate to features, such as ads, purchases, ratings, installs, and file sizes. Using FP Growth, we uncovered frequent permission combinations across the dataset. Overall, these results highlight key privacy risk and the need for more transparency and user awareness. Now dive into our third work, from Pandora's box to clarity. The introduction motivation for this work is that mobile apps request access to sensitive data, so users rely on privacy policies to understand what's being collected. But these policies are often hard and long and hard to read, so users tend to skip them. Even with regulations like CCPA or GDPR, many disclosures are vague or inconsistent. A key issue is that policies don't often clearly explain what permissions are used and why. Our approach uses NLP to classify permission-related policy segments. The goal of this is to boost transparency and support compliance with privacy regulations. Here's how the problem actually unfolds in real-world apps. Apps request permission for things like location, contacts, or storage. Then privacy policies are supposed to explain what data is collected and why. But in many cases, the policies are vague or skip some permissions entirely. This creates confusions for users and leads to transparency issues. The solution that we propose is to automatically detect these mismatches. We use NLP to classify the policy text and check if it properly reflects the requested permission. This helps align what apps actually do with what their policy says. Our main objective and goal is to use NLP to classify privacy policy segments based on app permission. This bridges the gap between what apps request and what they disclose in policies. The aim is to enhance transparency and help users understand data practices. For our contribution, we built an NLP pipeline using various BERT family models. We collected and cleaned permissions policy data from 5,000 applications. We grouped 40 permissions into 6 broad categories and labeled the segments. Finally, we evaluated multiple transformer models on this classification task. Now, moving to our workflow, it starts by app selections. We chose apps for analysis that ensure diversity and represent the dataset. We extract privacy policies and add metadata from these apps. Next, we clean and pre-process the text to standardized formatting. Then we extract permissions from these Android applications. Next, each policy segment is labeled based on the type of data is to close. Then the text is tokenized and encoded for model input. Lastly, we trained the transformer models to classify the labeled segments. Then finally, the output shows categorized segments, helping reveal gaps in transparency or compliance. Now, for data collection for privacy policies, we started with the 5,000 applications from the Troy dataset, which came from our prior work. To collect the privacy policies, we used the Google Play Scraper to query the Play Store by app ID. We then retrieved the privacy policy URL listed for each app. As shown in summary, out of the 5,000 applications, only 4,950 had valid privacy policy links. Only 78 apps were excluded because their links were missing or invalid. After getting the URL, we downloaded the raw HTML content using Python request and Beautiful Soup. Each policy was saved as an HTML file. We then cleaned the text using Beautiful Soup again and used Lang Detect to filter for English, such that any non-English content is removed. The final output was stored as a clean TXT file, all in English. At the bottom, the red bar summarizes what we removed, which are image-based policy, dead links, unreadable files, and unsupported formats. After that, we began data processing. We began by cleaning the text using the standard NLP techniques. First, we removed common words like the, and by using the NLTK library. Next, we filtered out special characters like @ $, and so on. We then split each privacy policy into smaller segments to reduce noise and improve model accuracy. Segments with fewer than 10 words were merged with the nearby ones to preserve context. Finally, we compute statistical counts on the cleaned policies. This example at the bottom shows how raw text on the left becomes 2 clean focused segments on the right after preprocessing highlighted in green. After preprocessing, we had a final dataset of 1,815 clean privacy policies. These policies contain over 97 paragraphs and about 3.69 million words in total. On average, each policy included 53 paragraphs and about 2,033 words. Now, this slide explains how we selected and filtered permissions for analysis. We used the same 5,000 applications from the Detroit dataset for permission extraction. To refine the list, we used the Android developers documentation to review each permission definition. We selected those relevant to privacy, data access, and security. We removed permissions that were redundant or less relevant to our study. That includes permissions like vibrate or set wallpaper. This gave us a final curated list of 40 permissions for our analysis. To better understand the types of permissions an app's request, we organized the 40 selected permissions into 6 semantic categories. Each group represents a specific aspect of data access or system functionality. The table lists these categories with examples and counts. Most permissions fall under the communication, messaging, and system and device setting categories. Now, this slide explains our first approach to labeling and our technical details. We first used keyword similarity. We manually created a keyword list for each permission. For example, the keyword location would be linked to the permission access file location. To showcase it from a diagram point of view, if a keyword match was found, a label was assigned. If no match, then the label was left unassigned. However, this approach contained many limitations. One of them is that it achieved high recall but low precision, and it caught many matches, but also introduced noise and some segments were mislabeled due to vague or ambiguous wording. This slide introduced our improved labeling method. Instead of simple keyword matching, we sent each clean segment to ChatGPT with a structured prompt. It chose the most relevant permission from a list of 40 options. Then we used human verification to validate and correct the outputs to ensure quality. This method captured vague or reworded descriptions better than keywords, but also reduced false positives and made labeling more consistent and scalable. This example right here shows how ChatGPT labeling method worked in practice. Let's say we had a segment from an application that says, we may use your voice commands to assist with in-app navigation. Pass that into ChatGPT with a very specific prompt and a fixed list of 40 permission options. ChatGPT returned record audio correctly, linking it to voice input. Then a human verified the output. In this case, it was accurate. If ChatGPT gave us a broad or incorrect label, we fixed it later. This is a semi-automated method, balanced speed and labeling in comparison to our keyword search labeling. So now let's talk about our technical details. We use transformer models as the core of our NLP approach. Their key strength is self-attention. They understand all words in context, not just in sequence. This is helpful for privacy policies, which are full of complex phrasing. For our main model, which was BERT, it's bidirectional, meaning it reads text both left to right and right to left, which gave us an edge in understanding legal language. We also tested other transformer-based models, such as Roberta, a faster and more robust variant of BERT, and DistillBERT, a smaller model that runs faster but sacrifices a little accuracy. Once the policy segments were labeled, we tokenized the text using the Hugging Face tokenizers, the same ones used by models like BERT and Roberta. The tokens were then encoded into numerical format for model inputs. After that, we stored the processed data into a compact format to make training more efficient. We then split the data. We used 80% for training, and the remainder, which is 20%, was reserved for testing. For evaluation, we used 4 standard metrics, as they are known: accuracy, precision, recall, and F1 score. Now, for the results, this slide shows the evaluation results for 5 transformer-based models. BERT Large came out on top with 91% accuracy and 91 F1 score, making it the strong performer. BERT Base followed secondly, and DistillBERT followed third, closely at a 90% F1 score, with DistillBERT offering faster, lighter training. These 3, BERT Large, BERT Base, and DistillBERT, clearly outperformed the others. Roberta Base scored an 86%, and Roberta Large, the lowest at 85 F1 score. We believe Roberta models underperformed due to the lack of next sentence prediction during pre-training, which is importantly for segment-level understanding. So overall, the BERT family, especially BERT Large, proved most effective for this classification task. After that, to improve the classification result, we used ensemble learning, which helps combine predictions from multiple models into one final output. In our case, we merged results from our best performing models. That includes BERT Large, BERT Base, and DistillBERT, our 3 top performers. Then we applied majority voting. Which label got at least 2 votes became the final prediction. This helped reduce errors. If one model misclassified a segment, then we relied on the other ones to override it. As a result, precision improved to 93%, while accuracy and F1 score stayed high, just like BERT large. For our discussion, BERT performed best. Roberta lagged behind, as we've seen, and Distilbert offered a good speed-accuracy trade-off. Ensemble learning improved precision and robustness. We show it's feasible to automate permission detection. For our limitation, our data is Android only, so findings may not generalize to other platforms. Preprocessing and segmentation decisions may have introduced bias or affected model accuracy. And then, large transformer models require significant compute resources. Despite using ChatGPT and human verifications, some label noise may still exist. As a summary, we started by collecting APKs and extracting their metadata and privacy policies. Then we filtered out and selected permissions related to policy content and grouped them into semantic categories. The labeling used ChatGPT suggests labels, followed by manual verification. Next, we trained multiple transformer-based models on the labeled segments. And finally, we compared their performance and used ensemble learning to improve classification result. Now, to conclude my presentation, we propose 3 work. First is Troid. We started with the dataset, which includes rich metadata for both benign and malicious apps, enabling security-focused analysis. We then performed a comprehensive analysis of permissions, tracking trends over time, genres, and relation with app features. We also applied FP growth to uncover frequent and potentially risk patterns. Lastly, we tackled privacy policy compliance by analyzing mismatches between requested permissions and policy disclosures, using NLP models to automate classification based on permission content. Here's the list of publications that contribute to my defense. With that, I conclude my presentation. Thank you so much for listening.